So you've spent all this time and energy training an AI model. But here's the big question. After all that work, how do we actually know if it's learned anything useful? Or did it just, memorize the answers to the test? Let's figure out how to tell the difference.
You see, a model can get a perfect score on data it's already seen, but that doesn't mean it's ready for the real world. We need to be sure it can genuinely generalize what it's learned, or if it's basically just cheating by peeking at the answer key.
Okay, here's our game plan. First, we're going to talk about why a perfect score isn't always what you want. Then, we'll get into the most important rule, splitting your data. After that, we'll see how to grade the machine's exam, and then dig way deeper with a cool tool called a confusion matrix and its visual sidekick, the heat map.
All right, first up, the problem with perfect scores. I know, it sounds a little weird, right? Why wouldn't 100% be a good thing? Well, in machine learning, a perfect score on the data it trained on can actually be a huge red flag.
And that red flag has a name. It's called overfitting. This is what happens when a model doesn't just learn the patterns, it starts memorizing every tiny detail, including all the random noise. And that's dangerous, because it completely falls apart when it sees new data. Think about it like a student who crams for a test by memorizing the exact answers to the practice questions. If the real test asks the same questions but in a slightly different way, they're toast.
So, what we're really after here isn't a perfect score on the study guide. The real goal is generalization. We need to build a model that can take what it's learned and apply it correctly to brand new data it has never, ever seen before. That's what makes it useful.
So how do we actually test for this? Well, that brings us to the absolute golden rule of machine learning. You have to split your data. You would never give a student a final exam using the exact same questions they had on their study sheet. It just wouldn't be a fair test.
And the process is actually pretty straightforward. You start with one big pile of labeled data. Then, using a really common function like train_testsplit in Python, you chop it into two totally separate piles that don't overlap at all. One pile is for training the model, and the other is set aside for testing it later.
This simple split gives us four really important pieces. You've got your training data, that's the model study guide, and the training labels, that's the answer key for the study guide. Then you have the testing data, this is the final exam. And finally, the testing labels, the official answer key for that final exam. And this is crucial. The model never gets to see this final answer key while it's learning.
Okay, so we've trained our model and we've given it the final exam. Now it's time to pull out the red pen and grade it. The first and most common way to do this is to just calculate its accuracy.
And the formula here is exactly what you'd think. It's just the number of answers the model got right divided by the total number of questions it answered. Pretty simple, right?
And here's what that looks like in practice. For every single item in our test set, we just compare what the model predicted with the actual true answer. You can see here the first three are spot on, but oops, on the fourth one, it missed. The model predicted decline when the real answer was admit.
So for this little example, let's say the model went through all 12 test cases and got 9 of them right. Well, 9 divided by 12, that's 75% accuracy. Okay, not bad, but is that really the whole story?
A single number, like 75%, gives us a nice high-level summary, but it hides all the important details. It doesn't tell us how it was wrong. Where did it get confused? Did it mix up admit with decline a lot? Or was it waitlist that tripped it up? To really improve our model, we've got to dig deeper.
And that deeper dive comes from this fantastic tool with a perfectly descriptive name, the Confusion Matrix. You can think of it like a really detailed report card. It doesn't just give you the final grade, it shows you exactly where the model did well, and more importantly, where it got confused. In its simplest form, a confusion matrix breaks down every prediction into one of 4 buckets. You have your correct guesses, true negatives and true positives, but the errors are where the magic is. A false positive is a false alarm. Think of a perfectly normal email getting flagged as spam, and a false negative is a total miss. That's when a really dangerous email slips right past the filter and into your inbox.
Now, when you first generate this in Python, you don't get a nice-looking table. You just get this, a raw array of numbers. I mean, all the information we need is in there, but just looking at it, it's pretty hard to spot any real patterns, right?
So how do we make sense of that block of numbers? This brings us to the final and maybe most satisfying step, turning that raw data into something we can actually understand. And we do that by visualizing it with something called a heat map.
And this is where Python libraries like Seaborn are just absolute lifesavers. Their whole purpose is to take complex data and create really attractive, good-looking graphs that make the insights just jump off the page.
Seaborn takes that boring array of numbers and turns it into this beautiful, color-coded and annotated heat map. All the correct predictions line up nicely on the diagonal. But the real story is in the squares off the diagonal. Those are the mistakes. A bright square off to the side instantly tells you, hey, the model is constantly confusing waitlist with decline. All of a sudden, that confusing block of numbers becomes an incredibly clear diagnostic tool.
So let's just quickly run through the key takeaways. Number 1, never ever test your model on the data it trained on. That's how you get fooled by overfitting. 2, always split your data for a fair test. 3, accuracy is a fine place to start, but it's never the whole story. 4, use a confusion matrix to find out the specific types of errors your model is making. And finally, number 5, use visuals like heat maps to make it all make sense at a glance.
And that really leaves us with a final, much bigger question. A model could be 99% accurate at spotting tumors in medical scans. But what if that 1% it gets wrong are all false negatives, telling sick patients that they're perfectly healthy? See, understanding where a model fails is often way more important than its overall score, and it forces us to ask that really tough question, what is good enough when we're counting on AI for these critical decisions?